Welcome back. In the last video, I indicated I was going to cover some object-oriented code. However, what I've decided is to change the plan and cover affine transformations first because they're actually used in the code. And then the following video would be the object-oriented design for the creation of the shapes. As I discussed in the last video, I have three regular polygons stacked on top of each other: equilateral triangle, a square, and a hexagon. In the lowercase here, they're all the same radius. In the uppercase over here, they're all have a similar equal side length. And lower down, I have a circle with an ellipse within it. I'm going to rotate this. The points are rotated with a 2D affine transformation. That's what I'm going to cover in detail. The circles are not rotated because they're symmetrical, and there'd be no purpose in rotating them. For the regular polygons, I could have done the rotation by just changing the starting point of the vertice calculation, but that isn't what I'm doing here. That wouldn't work for the ellipse because then you'd end up with the same ellipse. It wouldn't matter where you would start. Let's go to the next slide. Okay, I have two figures here, a rectangle and something I'm going to refer to as a bow tie. The bow tie is a polygon because you're allowed to cross lines for a basic polygon. It's basically a polyline that's closed, so therefore it's a polygon. The rectangle is a simple polygon. It's not a regular polygon because it doesn't have equal sides, even though it does have equal angles. I'm going to perform some affine transformations. I have a rotation, I have a scaling, and I have a translation. Let's go back. Three basic affine transformations, which I'm going to cover in detail. The most complicated one is the rotation. All right, there's four different affine transformations. Three of them you've seen in the previous slide. There's a rotation, there's a translation, which is just a change in position, it's a move. And there's a scaling, where you're changing the size of the figure. There's a shearing, which is basically an axis distortion. It changes the shape. It'll bend, it'll expand and compress. I'm not going to cover that one. The rotation is actually the most complicated mathematically of the three of them. And I'm going to be covering that in detail in the next slide. A translation is relatively simple. You're basically just changing the center point of the figure. And the scaling is just modifying the x and y component by a factor you're multiplying. The equation for a 2D affine rotation. And the two equations are shown here for the new y and x value as a result of the rotation. Now the complexity here is you really have two angles. You have the original angle and you have the rotation angle. Now looking at this from the point of view, if x was laying on the x-axis, the current x value would be actually a radius. So the rotation becomes quite trivial. If you look at the equation for x, then it would simply be x times the cosine of a, and there is no y component. That would just be the classic simple x and y values for an angle starting from an angle of 0. Same for the y. the y would be x times sine theta. Now keep in mind the radius is x when it's sitting on the x-axis. Now when you do have two angles, what is shown here is there's a difference that occurs in x, and there's a difference that occurs in y. Now I don't think you should try to bend your brain to try to calculate those, because based on the diagram. Because in actuality, the difference in x is based on two components, and the distance of y is also based on two components. Now what ends up happening is the angle A, which is the rotation, actually reduces the value of x by cosine A. Because remember, x is effectively the radius, and the change in the angle will give you partly a new x value of x times cosine. There's another reason it gets reduced, because remember I said there's two components. We have the sine value, and we have A, and the rotation of y ends up with a component here and a component here. Now that's a change in the x value. Now it's heading in the negative direction. Okay, and it's y times sine A. So x is both a reduction, because you got x times cosine A, that's standard, minus y times sine A. So they're the two parts of the change in x. Now there's a change in y. And y is actually both increasing and decreasing. Y increases by the x value times sine A, which is your standard situation even when, x is sitting on the x-axis. However, y also decreases because since it's moving left in this particular triangle, y is over here, it is going down. And it's going down based on y times cosine A, but it's still positive. So there's two terms here that are added together. There's the y cosine A and plus the y sine A. Now to some, this may end up just seeming completely obvious. For others, it's a little bit mind-bending. So actually focus on these two angles and start from the concept that the original x is sitting on the x-axis. Now if you give the previous equations some thought, you notice that the rotation is around an origin. In other words, it assumes the figure, whose points are being rotated, is located at a 0, 0 point. Now that's different than the origin in normalized space, which is 0, 0.5, 0.5. Now you've seen this figure before if you've watched the previous videos. And we did a rotation. What you'll notice is the figure itself is not exactly rotating. It's rotating around an origin. And the origin happens to be in the middle of the left-hand vertical. So in other words, it's rotating around that point, not the center of the figure. That means that if you do a translation, if you do a move before you do the rotation, you'll end up something different than if you do the rotation first and then the move. It makes a difference. In general, you define a shape based on a center, in other words, a 0, 0 point. And then you do a rotation, and then you do the translation. That's the standard way of approaching that. Now you're doing that in a different coordinate system. You're using an origin of 0, 0, not necessarily the origin of normalized space. And you'll see this when we go to the next slide in terms of how it's implemented in code. What I have here is the structure of what I'm referring to is a world 2D point. It's not a normalized space. It's generally just an abstraction out somewhere. It has an origin of 0, 0, and it could have points that are far out somewhere. In other words, they could be some distance from the center. It could be light years, it could be feet, it could be whatever. You'd want to take the resulting figure and you want to rotate the points. You want to scale, and you want to position them. And you want to do this in such a way that you can represent them within normalized space. And you do that with 3 affine transformations: the rotation, the scaling, and the translation. Now, given one of these points, there's a function defined as transformation. What it takes is a rotation value, a scaling value, and a point. In other words, where do you want to position it? Now you see here the equation with the cosine and sine values for the rotation. You multiply it by a scale factor. In other words, you generally want to reduce it down to normalized space. And you want to position it somewhere in normalized space. Now, potentially it could be 0, 5, 0, 5. It could be at the origin. Then you want to return that to your normalized point. So you can use this structure to define a figure which may be large. You can rotate it, you can scale it back, and you can position it. Now I'm going to end here. I just want to mention that transformations can be represented by something referred to as matrix algebra, or otherwise known as linear algebra. And I'm probably going to touch on that sometime in the future. It uses matrices to do the transformation calculations. And that comes into play much more significantly when you're talking about 3 dimensions. Anyway, that's it for this video. Have a great day.